Let's try applying conservation of energy to solve this problem. We have a block weighing 1.2 newtons. I'll go ahead and make a note as I read the problem that my weight is 1.2 newtons. From a spring with a spring constant of 6 newtons per meter, we'll call that K, as shown, and we want to know what's the maximum expansion of the spring as seen at point C. Okay, we have diagrams all ready for us. We'll say that if we're releasing this from rest, my initial velocity is 0. My final velocity at point C, before it starts coming back up, will be 0 at the maximum extension. And we want to know then, what is my y at point C? Let's try writing a conservation of energy statement. I'll be explicit and label this as conservation. Conservation of energy. And I'll even say between A and C. I recommend that you label where your principles and equations come from. You don't have to write out the full thing, but you can do like const period of energy or something. In order to do this, we have to neglect any non-conservative forces. So I'm going to neglect drag, which could exist here. It's going through air. We're just going to explicitly neglect that. There's no friction, so we can say that the energy at A has to equal whatever energy I have at C. I can be a little bit more explicit and say that kinetic energy at A plus the potential energy at A is equal to my kinetic energy at C plus the potential energy at C. We can be a little bit more explicit than that and include gravitational and spring potential energies, which means that we can say the kinetic energy at A plus the potential energy from gravity at A plus the potential energy from our spring or the elastic potential energy at A is equal to that same stuff at C. All right, let's write out what all these things are in terms of their variables. The kinetic energy at A is 1/2 mVA squared. The gravitational potential energy at A is mgYA. The spring potential energy is 1/2 KYA squared, because here the spring, how much the spring is stretched, is given by that same y coordinate. And that's equal to that same stuff, but now with velocities at C, y positions at C, and y positions still at C. We can go through and ask, do any of these things go away? And in fact, sometimes I might have done this already. I'm kind of writing everything out to be explicit. We know the velocity at A is 0. We set our y equals 0 here at A, which means that all of those terms go away. And my velocity at C goes away as well. So we're just left with 2 terms here. I'm going to rewrite this to say mgyc plus 1/2 kyc squared is equal to 0. In the worst case where we had other things, we might need to solve a quadratic here. But luckily, we only have terms that have yc's on them, so I can divide everything by a yc. 0 divided by yc just hangs out at 0. As long as yc is not 0 itself, we're fine. Which it's not. Explicitly, we know it's not. And now we can solve for the thing we want, yc. We'll move mg to the other side, so we get negative mg. And then we'll multiply by 2, divide by k, and we get yc is equal to negative 2mg over k. At this point, we can plug in our known quantities of mass. Well, mass times gravity is 1.2 newtons. And then k was 6 newtons per meter, which means that we end up with the newtons canceling. 1 over meters gives us meters, and we have negative 0.4 meters. And that's our yc. Lovely. Just using conservation of energy, we were able to figure out how far this thing would stretch from its original unstretched position. There's more. What about the potential energy at point B halfway between? Let's consider this point B. This is halfway between, so if I have negative 0.4, then this will be negative 0.4 divided by 2, or YB is equal to negative 0.2 meters. Okay, so now we can conserve our energy between A and B, or between C and B. So this will be between A and B, making the same argument that aerodynamic drag doesn't matter. And hopefully this will let us say what's the total potential energy there, and then what's the speed of the block at that point. EA equals EB. EA was 0 from before. EB is 1/2 mvb squared plus our total potential energy here. Actually, we can just calculate this. I'm going to write it out, mgyb plus 1/2 kyb squared. But this right here, this is all our potential energy at B combined, which means we can plug in the values for m, g, and yb and k and get our answer. mg we don't know separately, we know them combined as 1.2 newtons, which leaves us with negative 0.125 joules worth of potential energy at that point. Let's see if I can make a little bit better box. That's what you come here for, right? To watch me draw these boxes. That's the best part. Finally, we'll answer what's the speed of the block at point B. I think here, given that we know what that UB is, it's going to be easier to just write this as 1/2 mvb squared plus UB, knowing that I have a number for UB, and solve this for VB in terms of UB. I'll move UB to the other side, multiply by 2, divide by m, take a square root, and we get that VB is equal to the square root of negative 2UB divided by mg, right? Did I do that right? Let's divided by m. Oh, yeah. So we don't know m separately, but I do know g. So if I know, let's just do this real quick. mg is equal to 1.2 newtons. So m is equal to 1.2 newtons over 9.8 meters per second squared. So we know m, it's fine. We can plug in 4m here. And that gives us the square root. It's a square root of a negative there, but it's all right. Our UB is negative, so it'll cancel. Negative 2 times negative 0.125 joules. And then this will be 1.2 newtons over 9.8 over 9.8 meters per second squared. So make sure you get that nested division in there if you're plugging this in yourself. And we should end up with 1.4 meters per second as our velocity at B. I think that's kind of cool that we can find an expected velocity just halfway between as this thing is falling based on conservation of energy.